at first glance this question can look quite tricky, but in reality you've simply got an object that is moving in one direction, and that its position along that journey is measured in terms of x. It starts out at x0 here, which is at 10 meters, and in practice it begins to move in the negative direction along this x-axis. The force at any point in its journey is given by this graph. So when the object is here at x equals 10 meters, the force acting on it is minus 10 newtons. Similarly, in fact, all the way through to x equals 0 here, the force acting on it is always minus 10 newtons. So for this question here, what is its speed at x equals 0? Well, we just need to worry about this little section here, where the object is moving with a constant force being applied to it. So a constant force means a constant acceleration. So we first of all need to work out our acceleration. F equals ma, so therefore acceleration is the force divided by the mass. Our force here is minus 10, and our mass is 1 kilogram, so the acceleration is minus 10 meters per second squared. Now we can use the Suvat equations to work out exactly the position of the object. So let's begin by writing down our Suvat S here, the displacement. Well, we're starting off with a position of 10 and finishing at a position of 0. So actually the displacement here along the x-axis is negative, it's minus 10. Our u, our initial speed, is 0, it's initially at rest. V is what we're trying to find out. We've just calculated our A to be minus 10, and we don't care about T. So the equation we need to use here is going to be V squared equals U squared plus 2AS. We can immediately forget about U squared because that's equal to 0. So we're going to get V equals the square root of 2 times minus 10, which is our acceleration, times minus 10, which is our displacement. So we get the square root of 200, which is equivalent, if we use some surds now, equivalent to the square root of 2 times the square root of 100. This will just help us work it out a little bit. We know that root 2 is about 1.4, and root of 100 is exactly 10. So therefore V equals 14 meters per second. The next part of this question is a little bit trickier, worth 4 marks. It wants us to sketch the kinetic energy of the object as a function of x. So let's replicate these axes. I've just sketched the original graph here. Let's replicate these axes below. Kinetic energy on the y-axis, joules, and because kinetic energy is a scalar quantity, we don't need to worry about leaving room underneath our axis for negative quantities. So x in meters on the x-axis here. We're interested in the points there at 10, minus 10, minus 20, and minus 30. Now, how on earth are we supposed to work out the kinetic energy along this graph? Now, what's interesting here, of course, is that kinetic energy of the object is equal to the work that's done on it. The object starts at rest. All the kinetic energy it gains is as a result of the force acting on it over a distance. So, the kinetic energy equals the force times the distance moved in the direction of the force. Now, interestingly here, we have a graph of F against x. So we're interested in the area underneath this graph. So let's think about these first 10 meters here, as everything's working in reverse in this question. So the object is moving from here along this axis. So in these first 10 seconds, what's happening? Well, the area under this section of the graph is, so I'm afraid I haven't labelled this bit properly here, minus 10 here. The area under this section of the graph here is 10 times 10, which is going to give us a kinetic energy of 100 joules. and there's going to be a steady increase in that kinetic energy because there is a steady force being applied to it. So we can sketch this first part of the graph, a straight line up to 100 joules. Now, the rest of the graph is a little bit trickier. We know that something significant is happening at this point here. If you think about it, throughout this point, throughout this section of the graph here, there is a force being applied, albeit that force is decreasing, but there is a net force being applied, which means it's accelerating all the way up to this point. Then at this point, things flip around and it begins to decelerate because the force is being applied in the other direction. So therefore it must be increasing kinetic energy up to here and then losing it after that. So in other words, minus 10 meters on our x-axis here is going to be our maximum kinetic energy. So we know this is significant. Now, what's the kinetic energy going to be at that point? Well, to do that, again, we need to work out a little bit more area. So this area here is a triangle, 10 times 10 divided by 2, so that's going to give us an area of 50. So 50 joules added to 100, 150 joules is going to be our maximum kinetic energy that's reached by the time it gets to this point here. So we can continue our graph. We need to get up to this point here, so the graph is going to curve off to reach that point, and then the same curve should be then felt on the other side of the graph. And if you think about it, it should fall slightly short of 30 because of the nature of it curving rather than having a straight finish as it did in the first one. So if we can just continue the same trajectory of curve, we should get something that looks very similar to that. The next part of this question is very tricky because it's switching us from thinking about the motion of the object in terms of its displacement, x, into thinking about its motion in terms of the time, t. So we have to completely sort of switch our frame of reference and think about how it's moving over time. So the first part of our problem here is relatively straightforward. We know that it's got a constant force applied to it, therefore a constant acceleration. Begin by drawing some axes for our velocity time graph. So time in seconds on the x-axis and velocity on the y-axis, and we know that the object is accelerating at a constant rate for those first few seconds. However, we don't know exactly how long that's going on for, so we need to do a quick calculation here, again using SUVAT. That, by the way, is the only section of this graph where we're allowed to use SUVAT, because SUVAT, remember, only applies to constant accelerations. That's the only section with a constant acceleration. So let's write down what we know in terms of the SUVAT. We know that S equals minus 10 meters, that's the displacement, it's minus 10 meters along that x-axis. We know that the initial velocity is 0. We do know the final velocity from earlier, but just in case we made a mistake with that, we'll ignore that one. We know that the acceleration is minus 10 meters per second squared, and we want to know what the time is. So we can use S equals ut plus half at squared. We can lose that first term because u is 0. So we can rearrange this to get t equals 2s divided by a, and then we take the square root of that to give us t. So let's plug in some values here. That's 2 times minus 10 divided by minus 10. So the answer here is root 2, which is 1.4 seconds. Okay, so our first point of interest here along our axis needs to be at 1.4 seconds. And we know that during that time the velocity, remember it's a vector, the velocity is decreasing, the speed is increasing, but the velocity is decreasing because it's moving in our negative direction. So we can draw a straight line down to that point. Now this is where it gets interesting, because we can no longer use suvat to work out what's going on beyond this point in all this section here, because the force and therefore the acceleration is varying. Actually, to make my next explanation easier, I'm just going to swap the this axis on this original graph here from force to acceleration. We've already worked out earlier that the force of 1 Newton here is supplying 1 meters per second squared of acceleration, because the mass is 1 kilogram. So we can just pretend that that's acceleration on the axis, and it's exactly the same graph for A against X. Now let's ask this question again: where have you seen a graph that looks like this? In what context would you see a graph that looks like this for displacement against acceleration? And the answer is in simple harmonic motion. Okay, so an oscillating spring would have a graph of acceleration against displacement a lot like this, which means that the velocity against time graph is actually going to be sinusoidal. Now I can accept it seems a little bit strange for that to think like that and to get your head around it. So if you think about the motion of the object, so it's travelling along here and it's getting faster and faster and faster, and then from that point onwards its rate of acceleration is decreasing. So it's still getting a bit faster, then all of a sudden here it's gradually getting slower and slower and slower and slower and slower. So it follows that at some point up here the velocity will become positive, so therefore the object will begin to move in the positive x direction. So at least for one cycle, let's not worry about what's going to go on once it gets back down here, but at least for one cycle here, the motion is definitely that of simple harmonic motion, which we know to be sinusoidal. So we can sketch our graph to look something like this, with this section here a straight line and the rest of it sinusoidal. Now, okay, let's think about what an acceleration graph is going to look like. So let's sketch our axes again. Acceleration against time. Well, acceleration is the derivative of velocity, so it's the gradient of this velocity graph is going to be our acceleration. Once again, 1.4 seconds is important here, so let's mark that on. And for those first 1.4 seconds, the acceleration is constant, we know that, and also the gradient of this section is constant, so that matches with our derivative. Now, the derivative of a sine curve is a cosine curve. So let's very carefully sketch our curve here. So we need it shortly after the 1.4. We need it to go to 0. So these points match up. So that's the point at which the velocity is at its maximum. The acceleration is 0. That matches with our philosophy for simple harmonic motion as well. Similarly, when the velocity is 0 here, we should expect a maximum acceleration, and so on, with a sine curve that is going to remain 90 degrees out of sync with our velocity curve. This next part of the question describes how a frictional force has been applied to the object when x is greater than 0. So let's have a think about what that's going to do to the graph. Let's start by sketching some axes. So x displacement again against v velocity. Now we know that we're starting, as always, at 10 meters along on the x-axis, but what we don't know at the moment is what the velocity is going to be by the time it gets to x equals 0, because there's a different force being applied. The force here is going to be the original force, which is 10 newtons, take away the frictional force of 1 newton, so we're left with a force of 9 newtons. Now it's important that we've taken it away there. That's because this force is accelerating the object at this stage. The object is getting faster and faster as a result of this force, so the friction is going to work against that. So it's going to be 9 newtons. So we can use our equation from earlier, which is that the kinetic energy is equal to the work done. So K equals Fx. And the force here is 9,
the distance is 10, so the kinetic energy is 90 joules. Now using half mv squared again, I'm not going to go through all the steps to this. We get V is equal to the square root of 2 times the kinetic energy divided by the mass, which will give us the square root of 180. So at this point here, the velocity is root 180, and we can draw a straight line there to represent a constant acceleration up to 180. Now, as soon as you get to 0 on the x-axis, the frictional force stops, so the force beyond this is the same as it was before, and we've got that triangle of force. So the kinetic energy, the maximum kinetic energy we're going to reach over this next stage is going to be the same as it was before, which is the force times the distance. And it was a little triangle on our original graph, wasn't it? So we end up with 10 times 10 divided by 2, and following through the same steps as before, then that's 100. So we can add that to our previous kinetic energy, to get 190 joules. So our velocity is going to end up being the root of 280 joules, again, just using half mv squared there and rearranging. So we now know one more point in our graph, which is that the maximum negative velocity here is the root of 280 meters per second. So just as before, let's just sketch a line across there. As before, it's going to curve, it's going to reach that maximum, and then it's going to continue its curve until it gets here. So this is the point where v equals 0, that's where the object changes direction, it starts to move back in the positive x direction. So we'd imagine we get a curve that is symmetrical with the original one, so we can sketch that now like this, with it peaking at the same point here, and we know the value of that peak is going to be root 280, and we know that the point at which it hits the x-axis is going to be root of 180. However, this is where things get a little bit different. The force acting in this section here now is not 9 newtons, it's 11 newtons. Why is that? Well, the force is causing a deceleration. So our force of 10 newtons will actually be helped by the friction this time. So we can add that 1 newton. So we actually get a force of 11 newtons acting on the object during this section, which means we're going to get a steeper straight line going down. Now, if you can imagine this continuing indefinitely, you've now got a graph that's going to go like this, and back, and again, and back, and it's going to get progressively smaller until until the starting point becomes x equals 0, at which point it'll become stable and just constantly loop round. But that's our graph for now. We're going to have a think about where this point here is as our next question. So let's call that x1. So it's the x at the end of one oscillation. So the final question wants us to think about how many meters the object has travelled during the time when its position coordinate is greater than 0. So in that right hand side of the graph, just thinking about one oscillation here, not worrying about the oscillations backwards and forwards. So we know that it has travelled 10 meters in the first instance, and then on its way back it travels some other distance we've called x1. So how are we going to work out this x1? Well, we know that the work done is equal to the kinetic energy, and we know that the kinetic energy at x equals 0 was 90 joules. So that means that 90 equals Fx, and we know that F in that final section, remember, was 11 joules because it was the 10 joules plus 1 joule of friction that was helping slow down the object. So our x1 here becomes 90 divided by 11, which gives us somewhere around 8.2 meters. So therefore the total distance equals 10 plus 8.2 equals 18 meters.